All right, so that's for the component reaction selection. Now we move towards mineral reaction data. All right, we will add reaction parameters, and unfortunately we cannot expand this. All right, so you can follow me. So for anorthite, the reactive surface area is 88, also 88 for calcite, and for kaolinite it's 17,600 in meter square per meter cube. And then for the rate constant at reference temperature, you can follow me, it's minus 12, it's minus 8.8, it's minus 13. But for activation energy, energy will be involved to activate, to enable the reaction. It will be this based on literature. All right. Reference temperature will be 25 degrees centigrade. And this 62,760. All right, so far so good. And we will leave the rest as it is. And then here we will honor the Kozenik-Karman formula with the formula's exponent value of 3. All right, and then we will move forward to aqueous phase property models. And we select B dot model for aqueous phase activity model. Again, we need to understand about these models. You know, Pitzer model, simplified, Pitzer model, Debye-Huckel model, or ideal. In this case, we will use B dot model. Unfortunately, we do not have time to cover all these models, right? So, but for starter, you can follow me. And then let's see, you also have aqueous phase salinity. We will keep it as it is first. Hydrocarbon trace in aquifer, you can take if aquifer is completely filled with H2O and no trace hydrocarbon, but we will leave it as it is first. And then, yeah, click on OK first. All right, good. And then we will navigate onto the component selection. This one. All right, and then you see we have component here as per the selection. And then we move to, you know, this coefficient. And then we also have viscosity. We will follow all the defaults. And let's go to aqueous phase. Here we will define the, you know, the salt concentration, the sodium chloride, NaCl, all right, with the unit. And for that, we will use 0.1, but here it's the molality. So molality is the mole of the component that will be dissolved, okay, the NaCl, sodium chloride, per 1 kilogram of the liquid, which in this case is H2O. All right, and then we will use Harvey's method for Henry's law constant correlation, sorry. Yeah, we will use Harvey's. But again, we also have another option for Lingham's method, right? We have tried the two methods, Harvey's method and Lingham's method for Henry's law constant, which is very, very interesting and very, very important in guiding our CO2 dissolution. All right. And please note, the user, you can choose the option for calculation of salinity using Cl minus, the anion, or sodium plus, Na plus, the cation, or you can also use constant salinity if you want. In this case, again, I will use constant salinity, 0.1, in terms of the molality. All right, and now we go back to CMG gem. So don't forget to save all the progress. Go back to CMG gem, and again here, right, this one. and then aqueous phase models data. And you see here, use constant salinity, 0.1. And then here, aqueous phase threshold mole fraction. We need to read it together. Mineral precipitation or dissolution rates will be set to 0. Okay, if the mole of the gaseous component in the aqueous phase is less than the specified threshold value. So it's only threshold. Okay, threshold to here to set the precipitation rate or dissolution rate to be 0. All right, so it's actually you can have freedom for the methane, but for CO2, let's make it very, very small. So it means that you need to be very, very small. The CO2 need to be very, very small in order to stop the reaction for the precipitation or dissolution, okay? Which make it difficult, right, for the model to stop the precipitation or dissolution. So we will, in other words, so we will enable the precipitation and dissolution to continue with their respective rate, right, with the existing CO2 mole fraction in aqueous phase. So that's very good. All right, so I think we can click OK. And again, save. And in this case, we can run the model. All right, and then simulation graph or simulation output. Yeah, after this, we will move towards the next step, which is to deal with the gem. All right, but I think for the time being, we can stop it here. We can call it a day. In this specific video, we are dealing with the fluid modeling. Okay, we enable, some reactions in aqueous phase and mineral phase, which are very, very important in bringing this model towards mineralization trapping. Okay, so I think that's all. I hope you enjoyed this video. I hope this video is useful, and thank you so much for watching. See you again in the next CO2 sequestration modeling videos. Thank you.